What if I told you we could use quantum physics to make machine learning, well, exponentially faster, more powerful even? And no, we're not talking about those super complex quantum computers we always hear about. This is different. This is about taking like quantum thinking and applying it to AI as we know it.
Yeah.
It's exactly what today's deep dive explores. We're looking at this really cool research paper, right? And it uses this specific kind of tensor network. It's called a matrix product state, or MPS, to classify particle physics data. You know, the kind of data that comes from those massive particle colliders, sifting through all that noise to identify, say, a top quark. And you're probably thinking neural networks, right? They're usually our go-to for this kind of classification.
Yeah, definitely.
But they have this one big downside, you know. They can be a bit of a black box.
Yeah.
You get our results, sure, but understanding the why. Why did the network make those choices? It's a whole other story. And this is where quantum physics, surprisingly, comes in.
It's pretty wild.
The researchers behind this paper found a really interesting parallel. They suggest that just like a quantum wave function describes, you know, a particle's state, we can actually represent really complex data in a similar way using these things called tensor networks.
Right. It's like, imagine...
It's a way to break down those complex relationships into these smaller interconnected pieces.
Yeah, exactly. It's like you're building with Lego blocks, right? And each block, that represents a piece of information.
Okay, I like that.
The way you connect those blocks, that structure you build, it's like that dictates how the information relates within the data. That's essentially what a tensor network does.
So we're imposing this kind of structure onto the data to make sense of it.
Exactly. And an MPS in particular connects these blocks in a linear chain, like, think of it like building a long fence.
Okay, a fence as opposed to like a complex building or something.
Right. Not a complex structure, just a straightforward fence.
Got it.
Now, imagine those Lego blocks as particles. Entanglement in quantum mechanics means those particles are linked, like their fates are intertwined, even across huge distances.
That spooky action at a distance we always hear about.
Exactly. And MPS uses a similar concept to connect and weigh different features in the data. The strength of those connections, those weights, reflects how strongly those features are correlated.
So the stronger the connection, the more entangled those features are, the more they matter to each other.
Exactly. And what's remarkable is that this connection allows the MPS to adapt, you know? It can focus on the most important parts of the data for classification. It's incredibly efficient.
So it's kind of like having a filter that automatically gets rid of the noise and just highlights the important stuff, the key ingredients.
Yes. Potentially making it even more efficient than those traditional neural networks we were talking about.
So we're taking inspiration from the quantum realm to streamline and optimize our machine learning models. That's incredible. But how much more efficient are we really talking here? I know the paper compares this MPS approach to those more traditional methods like convolutional neural networks or CNNs, right?
Right.
What did they find?
So the results were really impressive. Even though the MPS, you know, it might seem limited because of that one-dimensional way of connecting information.
Right, that fence structure.
Exactly, the fence. It still performs surprisingly well, especially compared to CNNs in classifying this particle data. In some cases, the MPS needed way less processing power than a CNN while still being just as accurate.
Wow, so it's doing more with less.
Exactly. And the key takeaway is that the MPS achieves this by focusing on those local correlations within the data. It's like analyzing neighboring pixels in an image to figure out what the whole picture is.
I see, it's picking up on those subtle relationships.
Yes. By zeroing in on those local relationships, the MPS manages to capture the essential information for classification. And that potentially makes it faster, much more computationally efficient than CNNs, especially when we're talking about those massive data sets we see in particle physics.
That's amazing. It's like the MPS is cutting through the noise and getting straight to the heart of the matter. But there's one more piece to this puzzle I'm dying to unpack, this idea of entanglement entropy.
Ah, yes.
The paper uses it as a tool to actually understand what the MPS is learning, which sounds incredibly complex.
It is complex, yeah, but it's also incredibly elegant.
Okay, I'm intrigued.
So think about it this way. In the context of MPS, entanglement entropy is a way to measure how much information a particular Lego block, that node in the network, actually holds.
Okay, so how important that piece of information is in the grand scheme of things?
Right. The higher the entropy,
Yeah.
the more strongly it's correlated with other blocks, the more vital it is to the network's understanding.
So it's like identifying the VIPs, the most informative parts of the network, the ones that are really driving the classification process.
Exactly.
But how does this help us in a practical sense?
Is where it gets really interesting. By analyzing this entanglement entropy, the researchers could pinpoint and discard less important connections in the network, effectively compressing it without sacrificing much accuracy.
That's incredible. It's like taking a giant library and condensing the most crucial information into a single book.
Precisely. And this ability to shrink the network without losing accuracy, that's a game changer. We're talking about computational resources here. It means we can potentially achieve the same results with less processing power, less energy, less time. Yeah, it's all about getting the most bang for your buck, right? Maximizing that efficiency without losing sight of accuracy. But what's really cool is that this approach, it's not just about making our current AI better. It kind of hints at this deeper connection, between quantum physics and machine learning.
You're right. It feels like we're just scratching the surface here. We're using these quantum-inspired methods to kind of shake things up in machine learning. But could this go both ways? Could we actually use AI to understand the quantum world better?
Now, that's a question that has a lot of researchers really excited, I'll tell you. Imagine using machine learning to analyze how quantum systems behave,
To really dig into that data and
find patterns, make predictions that are just like beyond our current theoretical understanding, or even using AI to design completely new quantum experiments. It's not science fiction, it's a very real possibility.
that's mind-blowing to think we could crack open some of the biggest mysteries of the universe using AI. But let's bring this back down to Earth for a second. This research, it focused on classifying particle physics data, right? But what about other applications? Where else could this MPS approach be useful?
That's the beauty of this kind of fundamental research. It's like throwing a stone in a pond. The ripples, they spread out. It often has these ripple effects across different disciplines. While this specific paper, yeah, it focused on particle physics, the underlying principles, they're universal. They could be applied to any field that involves analyzing these massive, complex data sets.
So we could be talking about like anything from medical diagnosis to financial modeling, even understanding those complex climate patterns.
You got it. Anyway, you need to extract meaning from large, intricate data sets, this quantum-inspired approach could be a game changer. Imagine doctors being able to diagnose diseases way earlier and with much greater accuracy, or financial analysts making smarter predictions about the stock market.
It's amazing to think that by borrowing from the quantum world, which often feels so counterintuitive, right? We can potentially make our AI systems smarter, faster, and way more efficient. And who knows, maybe we'll even end up understanding the quantum world better in the process, right?
Exactly. It's like we're using one of the universe's biggest mysteries to solve other mysteries.
It really highlights how interconnected all these different fields of science really are. Like, we often think of them as these separate things,
Yeah.
but it's when they overlap, when they connect, that's when the really cool stuff happens.
Absolutely. I mean, this research is the perfect example. We're taking quantum physics and artificial intelligence, bringing them together, and suddenly we've got all these possibilities that we could have only dreamed of before.
It's like we're using one of the universe's most intriguing mysteries, quantum mechanics, to unlock even deeper mysteries.
And the best part, we're just getting started. As we keep digging into these quantum-inspired approaches, who knows what other breakthroughs are waiting for us. It's a really exciting time to be working in these fields.
Absolutely. It makes you wonder what other unexpected connections are out there, just waiting for us to find them. Well, this has been an amazing deep dive. Thanks for walking me through all of this incredible research. It's really changed how I think about the potential of quantum-inspired machine learning.
My pleasure. I always love talking about this stuff. It's just fascinating.
And everyone listening, thanks for joining us on this deep dive into the world where quantum physics and AI collide. We hope you come away with that same sense of wonder about the future of science. Until next time, keep those minds curious.